down. I did both. Yes, now it works. And before I start, I just want to show you the problem we target. So in the classical cryptography, we often use the black box model, where the adversary only learns about the input-output behavior of cryptographic primitives, for example, the message ciphertext pairs of encryption schemes. And in the real world, the adversary is much more powerful. Yeah, as you saw in the first presentation, it can learn some information about the internal computation via side-channel attacks, for example, by measuring the power consumption of a device, or can even insert faults via fault attacks. You can think about inserting some electromagnetic pulses in the computation. And we want to target these problems. And therefore, we first have to model those attacks. And for this, we've started with a computational model to describe the inner computation. And there we use the circuit model, yeah, where each operation is described as a gate and all values are carried by wires. And with this, we can first define the leakage model, where we allow the adversary to probe the wires to learn the values that they carry. And also, we can define a fault model, where the adversary can choose E wires and fault the values they carry. And in our work, we combine both models and give the adversary the right to do both probe D wires and fault E wires. How to protect those attacks? We first only protect the data. Yeah, I show you how to protect or how to encode the secrets to make it resilient against those attacks. And the first one is the duplicated encoding. Here we first share the secret into D+1 out of D+1 sharing. This means that even when we probe the wires, we do not learn anything about the secret. And then we can copy each share E+1 times. This means that even when we fault E wires, there is still one unfaulted wire, and we can detect again the faults. This would require D times E shares. And an alternative way is Shamir secret sharing, where we use D+1 out of D+E+1 secret sharing. This means that, again, if we probe D wires, we do not learn anything about the secret, but also if we fault E wires, we still have D+1 unfaulted shares and can decode to the correct secret and can therefore also detect the faults. The second one only requires D+E shares. This means that it needs much less shares, and that's why we consider Shamir secret sharing in our work. And now I will show you how to also protect the circuit against those attacks. So therefore, we take the unprotected circuit, we encode the inputs and secrets, transform each gate into sub-circuits that only compute on the sharings, such that they still have the same functionality as the gates. And yes, and we call these sub-circuits also gadgets. And we can even insert some internal randomness that does not change the functionality of the computation, but re-randomizes the inner computation. Okay, so once I have shown you how to compile those unprotected circuits into protected circuits, I give you some state of the art. So to use these Shamir secret sharing and to protect the circuit against D-probes and defaults, they were already done two compilers. The first one requires 2D plus E+1 shares and has a complexity of n square for the gadgets. The second one requires a tight number of shares, D plus E+1, but requires a much higher complexity. And that's actually what we target. So we wanted to use the tight number of shares and still have the complexity of n square. And this is what we achieved with our compiler. And therefore, I will now show you the overview about, and we even improved the security because we do not only allow the adversary to probe D wires in the full circuit, we even allow D half probes in each gadget. Means that we can increase the number of probes with the circuit size. Okay, so next I will just give you an overview about our paper. So as I said, we generate new gadgets. Then we prove that they are leakage resilient and fault resilient. The first one we do with these classical leakage simulators. And the second one we do with a new definition, fault robustness, that allows us to say that if a gadget gets invalid encodings as inputs and has some internal faults, it also outputs invalid encodings. Then we show that, unfortunately, both considered separately do not imply immediately combined resilience. That's why we also give a third definition, the fault invariance, that allows us to lift both resiliences up to combined resilience. So for more details about these two definitions, I would like to refer to our paper. And now I will focus on the multiplication that we use. Therefore, I just recap the secret sharing. To encode and secret, we just choose a uniform random polynomial of degree d with a constant factor s and output n of these function values that are the shares. And to decode, we just need to compute the constant term of the polynomial. And this gives us this d-wise independence of d shares due to the randomness of the polynomial, and also the fault resilience, because when we have d plus e plus 1 shares and we only can fault e values, this automatically leads to a degree to a polynomial with a higher degree than d, and we can detect the faults. So now I will just show you how to compute with these encodings with the gadgets. And the first one is the addition gadget, which is quite easy. It's just shareways addition. So if we have an encoding of A and B, we just need to shareways add them together to get the addition. This just follows from the polynomial properties. And the refresh I just showed you before, that re-randomizes encoding that such that the decoding is still the same, is simply taking as input this encoding of A, generate an encoding of 0, and add it to shareways added to the A, and this is then a refresh. In our paper, we show that this simple construction has an attack. For the details, I would like to refer to the paper, but we also provide a fix because we have to generate D encodings of 0 to have the security properties that we need. Okay, so the next one is the multiplication. So with this, we can already compile affine circuits with plus and refresh. And now we want to move to the generic construction. And here we need a multiplication. And for this, we can also take an encoding of A and B and shareways multiply it. But then we get a non-valid encoding, I would say, because the product of two polynomials is of degree 2d when the original polynomials are of degree d. And this means that when we multiply it shareways, we still have to do the degree reduction from 2d to d. And actually, that's the case why the first compiler is not tight in the number of shares, because due to this intermediate polynomial of degree 2d, we require a number of shares of 2d plus e plus 1. And this we want to fix in our multiplication. So we thought, okay, why do not reverse the steps? Yeah, instead of first shareways multiply and degree reduction, we do first the degree reduction and then multiply. Unfortunately, when we do it in that way, there's an attack because we have this intermediate polynomial of degree d half, means we can reconstruct the secret of this intermediate value with less than d props. But we still use this high level idea, but we use a split red gadget that generates two polynomials, a prime and a prime prime, such that when they sum up, they are exactly this degree d half polynomial of A. Okay. So how does it work in our multiplication? We first use the split that gadget for A and B to generate A prime prime, and B prime, and B prime prime. And then we shareways multiply each combination, A prime, B prime, so on, so on, so on, and add them all together. And this is our result. And why is this correct? Because we can transform this equation in that way. And now remember the property of our split reduction. This is exactly the A of degree D half and B of degree D half. And when we pairwise multiply this, it's A times B. Okay, so this shows us the correctness of our gadget. For the security, we still need some randomness there. So the first one we need to do is we refresh the output, and we also insert some randomness in the split red gadgets. Means this how we do it in the split red. We do it in the same way as we do it in the classical degree reduction. Yeah. Okay. So how to prove now this multiplication gadget, the security? We first show this fault robustness. This was the first definition I gave you. So there we prove that even if we insert there if intermediate false and give the gadget an invalid encoding that causes by false in the previous gadgets, we guarantee that the output C plus delta C, so C you can see as the original unfaulted output of the gadget, and this delta is the effect of the false. And we can prove that this delta C is either of a higher degree, means larger than D, and we can detect the fault, or it's simply an constant zero polynomial, hence there is no effect of a fault. And this allows us to provide fault robustness. And for the combined resilience, we had this E-fault robustness I showed you before. Then we prove this deprobing security that we just do as in the classical masking of circuits. And then we show this fault invariance that allows us to lift up the fault resilience and leakage resilience to the combined resilience. And how do we do this? So we show that we can describe each intermediate value as a function that depends on the inputs of the gadget. Okay. And then we also describe the according value, intermediate value of the faulted gadget. It's F prime. And then we show that we can describe this faulted function with the function of the unfaulted according prop in the that the faulted the faulted value of the faulted gadget F prime can be described as a function of the intermediate value, according intermediate value of the unfaulted gadget. Only that we have to apply some functions on the inputs and on the outputs. And how can you imagine this? It's like if you have all the faults in the gadget and you can see it as, okay, we move all the faults to the inputs or to the output, the effect of the faults, okay? And with this technique, we can reuse the combined leakage compiler, leakage simulator of the simply probing security to the combined resilience. Means that we proved A, B, and C for our gadget, and this implies combined resilience. And yes. So what I said, so this was what we did in the paper. So we had this fault robustness and fault invariance and the leakage simulator, and we proved this for the multiplication, addition, and refresh. And then I showed you how the multiplication worked for our compiler. And yes, with this I want to thank you for listening, and any questions are welcome.
Thank you very much for the presentation. We have plenty of time for questions. So if you do have questions, please feel free to come forward or log into Zoom and ask your question. Then I'm happy to read it out. I can start with the first one where you were thinking. Okay, so it's very nice work, and I wonder how generic the approach is, or are there any limitations to your approach?
Yes, we have these limitations that we allow D props and E faults, and this means that that we can do their arbitrary faults on the wires, but only on E wires, and the same with D props. So we can prop arbitrary D wires, but only D wires. Or in this extended version, where we prove that we can prop in each gadget D half wires. We have still this restriction of the threshold, but that's the only restriction.
Thank you. Please.
I'm curious, especially in the context of the last talk, about like what a real world fault injection attack would look like and how that would compare to the E fault model that you're using.
Yeah, that's a good question. What I know is that it's maybe not the ideal description of a fault, but it's the first way to model this fault robustness or this resilience of faults. I would say, I mean, we say that we can only fault E wires, but maybe in the real world, we also have the case that maybe we can not only fault one specific wire and only fault a group of wires. That could be somehow an extension how to extend the model. Yeah, and also to how it's related to the leakage model of the talk before. That's exactly where we have these that we allow D half props in each gadget, because this allows us a better implication to this noisy model that was presented just before, where the noise, or not the noise, but the leakage increases with the circuit size. Yeah, but this is what we actually do with where I showed you. Oh. Here, yeah, the last step where we said, okay, we allow D half prop in each gadget, because then, yeah, we also have this fact that the leakage increases with the circuit size.
Thanks, nice talk. I have a question: how efficient is it, or how many multiplications, additions, and random do you need? For example, if you have 3 shares and 1 fault.
So that's exactly what you can. So when we go to the multiplication,
with the reduction, I don't know exactly what you do there. The split red, I don't know how expensive that is.
Quite efficient, I would say, because it does not use. So I mean, we can distinguish between multiplication with constant and multiplication of 2 variables, and the only multiplications of 2 variables are in that share-wise multiplication. Here we only multiply constants or do additions. Okay. So that's why we here have only n 4 times n 4 times n multiplications.
And how much random?
And randomness is in complexity, it's n squared. But 1 second. That's what you can see here. We have generate these n encoding of zeros of degree d half and n half of degree d. So this means that we have n times d half plus n½ times d, which is n times d, plus d times d. So it's
Okay.
2 times d
Thanks.
squared. Welcome.
Are there any other questions? We still have a couple of minutes. If not, then we can have a long track switch. Let's thank the speaker again.
Thank you.
So it's now track switch break, and we'll